Welcome to the aiT product demo. I've selected the Infineon Tricore AURIX architecture in aiT to show you how aiT looks like and behaves for computing worst-case execution time bounds. For that, let's start from scratch with an empty project by selecting first the executable program. And I've selected precompiled binary here. It's called scenarios acube.elf file. Next step would be the hardware configuration in aiT. You have to know that the aiT has to be configured in the very same way as the real hardware, wherever you have parameterization. So in this case, it's a binary for the AURIX 275 target, and this comes with certain memory units and parameterization, which I keep for a moment with the default values. But for your real project, you always have to configure the aiT in the very same way as you have configured the real hardware. Next step would be, well, to provide an entry point for the analysis. And for that, we first select a new aiT analysis item here. You see it will automatically create it with an ID called aiT. And it indicates us to select as a next step the analysis starting point. And by clicking on this pipette symbol, the entire symbol table of the binary will be extracted. And now we could search, for instance, for individual tasks like, let's say the task 10 milliseconds try, which is a benchmark task that could be interesting to analyze. So let me copy that one here, also into the ID field. Maybe we put a nice aiT suffix here behind, so that we directly see on the left side in our list of individual task entries what we are actually analyzing. So next step would be a bit of configuration again. Under setup files, I have prepared a global specification AIS file, and that would be the scenarios acube AIS. I can show you what's inside. So the first specification is compiler specification, which can also be auto-generated here via the context menu, insert ICE annotation compiler, and then you can select your corresponding compiler, which has been activated in the license. In this case, the binary has been produced by the GCC compiler. And the next one is the clock rate of the CPU. In this case, in this example, it's 100 megahertz. This can also be, by the way, generated via the ICE context menu. All right, now we are in a position to start the very first analysis already. So we could go here and click on this play button. This will start the WCET analysis of the selected item. The fast forward button will start all analysis items. Well, we just have one currently. And this one is the interactive start for the selected entry point, which has some additional benefits, which I could show you in a second. Before starting the analysis, we should probably save the project first. We could use here a predefined project and overwrite that one. This is having the extension APX, collecting all references that we have done so far. So the executable is referred, the global ICE specification file, and the one analysis item, as well as the hardware configuration, has now been saved to this project file, right? Let's start the interactive analysis of the 10 millisecond task. For that, I'm clicking here. And the different analysis stages, which I've presented in my talk, will be executed after each other. So the control flow reconstruction, the static value analysis, the microarchitecture analysis, the cache and pipeline, which determines worst case timings for individual instructions, and last but not least the path analysis, which in this case indicated or reported some warnings here about unbounded loop bounds for various loops in this 10 millisecond task, and whenever this was or static upper bound could not be determined, we apply a default of 4 in order to compute the worst case time estimate in any case. But the rule of thumb is, as long as you have at least a warning or an error message during the analysis, the result is not yet final, and so also not yet safe. So in this case, we have calculated 477.39 microseconds based on these default loop bounds. But we can also visualize the code, the call and control flow graph. It looks like this. Here again we have the result and also small cache statistics in this case. And the call graph, which consists of routine nodes and call edges between these routines, while these edges only indicate the call relation and not the call frequency. So especially you can have just one edge, call edge, but the function can be called more than once. Also contained in the call graph is the information about the contribution of each routine to the overall worst case execution time. So in this case, the entry routine contributes just 860 nanoseconds. The next routine, try, already 1.54 microseconds, and proc 0 66.7 microseconds, and so on. Each contribution of a routine is also visualized by that red bar here. All right, and then we have the call edges, which all of them are red here. That means all these calls are lying on the worst case path. I can show you later an example where you have an alternative between two paths. But before we continue, let's fix that issue with that unbounded loops. I know this benchmark very well, and I know the solution by simply by simply unrolling all the loops more virtually, we can find a bound statically, so especially without the need for the user to annotate them. For that, we can go to the ICE file and add another annotation. So we can go here, ICE annotation, context, and improve or increase the so-called mapping parameters, and especially the unroll parameter, where we by default distinguish just first iteration of a loop from all others. We could increase that to, in this case, 50. I think this is enough to unroll all the loops virtually during analysis. And if we come back to the analysis and restart it, you will see the effect. So there is no longer a warning message. That means all loops have now been are bounded, and in this case the analyzer could even improve our first estimate down to 326 microseconds. And now that we have no longer any warning or error, the result can be seen as a safe and precise upper bound on the real worst case execution time, right? And by the way, now that we have increased the mapping parameters, the default unroll, but also the max length to infinity, we are also able to compute the so-called cumulative worst-case execution timing information. So, and especially if we go to proc 1, we not only see the red bar indicating the 7.83 microseconds, but we also visualize the orange bar that basically accumulates the contributions of the children routines. In this case, proc 6, I think proc 7, and proc 3 and memcopyx. This is the information you can see on call graph level, but you can also enter the control flow of routine, and this looks like this. By double-clicking on a routine node, you enter the control flow graph, and well, here we visualize the basic blocks, and if we know if the binary has been compiled with dwarf debug information, we have the reference to the original application code, right? And if the source code, the application code, is also accessible on the PC, on the machine where we perform the analysis, then we also visualize that source code belonging to this basic block. If this is not available, you can at least or visualize the machine instructions which are behind this basic block, right? So these are tri-core AURIX machine instructions, and this basic block ends with a call to the memcopy routine. After each of such a basic block, we find a timing node on the worst case path actually. And this timing node indicates how often this basic block is executed and left by this edge here in the worst case scenario. In this case, it's only executed once, and the worst case timing contribution of that basic block consisting of these machine instructions is 95 cycles in the worst case. There might be some other contexts where this function is executed, which would lead to a different timing contribution, but at the worst, it's just 95. Now you can follow that call to memcopyx by clicking on the context menu here and say go to target memcopyx. You immediately jump to the memcopyx routine, and you can encounter why this routine contributes so much, namely 68.3 microseconds to the entire worst case execution time. Well, this is probably because we have a loop here inside that copies some data from source to destination, right? Okay, coming back to the caller here in proc1, we follow the worst case path, which is indicated by this halo edges, this red halo edges, to the next basic block, which is left by call to proc3. And then we have an if then else statement, which checks if some variable next record.disk equals the ident1. In this case, the analyzer could prove that the else branch can never be taken in the given situation. It could really prove that this code is infeasible, so we have found a dead code in the current configuration, and have to follow the then case, right, where we call proc6, proc7, and so on. And here we complete the execution of the proc1 routine. If the analyzer was not able to prove that this branch is infeasible, we would have two alternatives here, and the analyzer would select that path which would lead, globally seen, to the worst case timing, right? In addition to the call graph visualization, you also get a lot of information in our statistics view. By clicking on that button here above, the statistics view will be opened and showing you in the first category here an overview about the WCET contributions of each routine and loop in the analyzed task with its self contribution, self cycles, and here in a timing unit, and also percentage contribution, which you can sort for. So you immediately see also in this table which components, in this case the three loops here, dominate the worst case timing. But you also see the cumulative contribution, right? Of course, the entry routine, if there is cumulative information available, the entry routine will always have 100%, since the self-contribution plus the contribution of all children routines will together be the cumulative, right? The cumulative contribution. We also have that overview context specific, so you can follow here the individual calling contexts. 10 millisecond task, the entry routine calls the try routine at this address. At this address here in try, we call proc0, and we have a certain self-contribution here, and so on. The proc0 calls malloc x twice, string copy x twice, and some bigger loop. And for instance here, you directly see that the string copy here is called in two different contexts out of the very same routine, and we distinguish here the different timings. We have once 100 cycles, and in the other context 3 cycles more. If we do not distinguish these cycles, we would have to select 103 as the worst case and multiply it by the number of contexts we distinguish, right? So this could lead to more conservative, less precise results. But we do a distinction here on each individual context. Furthermore, we have an overview about the loop bounds that we found out in the analyzed task. So in this case, we have 2, 4, 6, 8, 9 loops, and all of them could be determined statically, as we have learned by unrolling the loops virtually completely. Here we have 45 iterations, 31, 20, and so on. And if a loop was not detected automatically, and even if the unrolling did not help, the user might use, or you will see here, an infinite loop bound, and can use again the context menu to provide a loop bound annotation to copy it to clipboard and enter it to the ICE file and extend it by providing the upper bound. In addition to this information, we also provide variable usage information for global variables that are accessed on the worst case path. Especially, we count how often these global variables are read and written to on the worst case path. And this can be a valuable information, for instance, to optimize access to shared resources, right? And this information is also available context specific. Yeah? Okay. Yes, so this basically concludes already my demo of the AIT. Of course, there are many more to show. So, for instance, there is also an output, available, output mechanism available. We have a textual report file that gives you a lot of information on what has been analyzed, what are the results here in the different categories. The same information can be written automatically to an XML format, also to an HTML format, which will be opened in your favorite browser. Gives you a compact view on which version has been used and what was the worst case timing, and this table which we have seen here in the HTML format, and last but not least, how many warnings and errors were left in this analysis. And another nice feature is using an expected result. So here you could enter your deadline that you have reserved for this 10 millisecond task. For instance, you could say I have used not more than let's say 350 microseconds, and of course, since we have a worst case bound of 326, this will not violate our limit here. No? And so you can observe that in a continuous environment, and if suddenly the timing increases or your allocated time slot shrinks, so let's simulate that, you will immediately be noticed by some assertion violation basically, and you will find that in the report output or in XML result output. All right, this concludes my demonstration. I hope it was interesting for you. If you have any more questions concerning IT, please feel free to contact us via info@absint.com or access our website on absint.com. Thank you very much. Take care. Bye-bye.